So Keras is turning 5 next month. So in a few days, they grow up so fast. And so lately, I've been thinking about the next 5 years. So I'd like to talk about where we are now and where we're going next. What are we going to be building for the next 5 years? And before I talk about Keras, let me say a few words about TensorFlow. There would be no Keras without TensorFlow. TensorFlow is really the foundation on which Keras is built. And I feel like many people have misconceptions about TensorFlow. People will say, TensorFlow is a Python-based deep learning library. And that's not quite right? It's not just Python. It's not just deep learning. And importantly, it's not a library. It's more of a platform or an ecosystem. So the way I think about TensorFlow is as an infrastructure layer for differentiable programming, right? And so I've been thinking about these things and working with TensorFlow for the past 4.5 years. And the more I've been working with it, the more I've come to think that TensorFlow is really the infrastructure of differentiable programming applications for the next 20 years. And that's been the case for a few years, but it's going to be even more true in the future. And so TensorFlow combines 3 things. And the first one, you all know about it, of course. It's tensor manipulation. So TensorFlow is a kind of NumPy, in a way. With one big difference with NumPy is that you get gradients for free, pretty much. And it's pretty flexible. You can get gradients of gradients of gradients, and so on. So it's basically NumPy with gradients. And another big difference with NumPy is that besides gradients, TensorFlow scales, right? You can run TensorFlow on hardware accelerators like TPUs, GPUs, and so on. And so you can also run distributed training, distributed inference out of the box. And here's one example. So the picture you're looking at here is the Summit supercomputer. So built by IBM, it's made of 27,000 NVIDIA GPUs. So that's a lot of compute. And so researchers at Oak Ridge National Lab, they're using it to model and predict extreme weather, right? Which is a very, very tough problem. So the scale and complexity of the data involved is really high. And so they built a very sophisticated deep learning architecture to handle that. And so it's all built with TensorFlow. So it's trained on these 27,000 GPUs. And so they got a peak of 1.13 exaflops. And that's the largest deep learning model ever built. So TensorFlow scales a bit better than NumPy. And one last difference with something like NumPy is that it's not just Python, right? So you can export TensorFlow programs and run them pretty much anywhere. You can run them in C++ on a server. Of course, you can run them on an Android or iOS device. You can run them in a web browser, in JavaScript. And you can even run them on a microcontroller. So that's really how I want you to think about TensorFlow. What I want you to know about TensorFlow is that it's this infrastructure layer for differentiable programming. It's not just a Python library or something like that. It's not just deep learning. So now let's take a look at Keras. So what's Keras all about? What's the difference with TensorFlow? Since we already have TensorFlow, why would we need Keras? What's the relationship between Keras and TensorFlow? Well, Keras and TensorFlow have had a symbiotic relationship for many years. Keras serves as the high-level API for TensorFlow. So it's basically the interface that most people are going to be using to solve machine learning problems. And so you may ask, why does TensorFlow need a high-level library? Why not just stick to the low-level library? Well, Keras is basically what makes TensorFlow accessible and productive. While TensorFlow is basically this infrastructure layer that handles things like tensor manipulation and gradients and distribution, Keras is this UX layer for deep learning. And UX is actually hugely important, right? I feel like UX is often a neglected aspect of software, of developer-facing tools in particular. I often encounter the belief that software tools are only about making things possible. They're not about making things nice or productive, and I think that's wrong. I think UX is actually hugely important components of any software tool. And here's why UX matters. If you want to build something great, well, a factor that's critical is the speed at which you can iterate on what you're working on, right? And let's say you want to win a data science competition, for instance. Well, it's not the smartest person who wins. It's not the person who started out with the best idea. It's actually just the person on the team who was able to iterate the most times on their initial ideas. And so in deep learning, iteration cycles depend on 3 factors. You start with an idea, and then you use a deep learning framework, software framework, to implement an experiment to test your idea. Then you run that experiment on hardware accelerators, maybe a data center. You get some results, and then you visualize, you analyze your results to try to gain some understanding about what your experiment really meant. And that feeds into the next idea, right? And developing great things, great ideas, depends entirely on your ability to go through this loop as fast as possible. And so there are 3 things that are really going to be important. The first thing is you want a good visualization framework, something like TensorBoard or even better than that. Then you want fast infrastructure, right? You want bigger GPUs, you want bigger data centers, and so on, to run your experiments as fast as possible. But then you also want a deep learning framework with a great UX that enables you to go from idea to experiment as fast as possible. And that's what Keras is. That's what Keras is all about. It's a medium for expressing ideas about deep learning experiments as fast as possible, as easily as possible, with as little friction as possible, with as much flexibility as possible. That's really what it's optimized for since the beginning. And lots of people will tell you, because Keras has this focus on UX, it's mostly good for beginners because it's easy to use. And I think that's a really bad take, actually, because the people who stand to benefit the most from good UX are not the beginners. It's actually the very best deep learning people in the world, because good design makes you more productive by minimizing the friction there is in trying new ideas, right? By minimizing iteration time. So the more ideas you try, the more progress you make. So good design means faster progress. It translates directly to shorter iteration times and faster progress. So for instance, winning machine learning competitions, deep learning competitions, it's basically a game of iterative idea refinement. And so last year, towards the end of last year, we did a survey among competition winners on Kaggle. So among teams that ended up at least in the top 5 of any competition between basically 2017 and 2019. And we asked them what framework, what machine learning framework or library they were using in that competition in which they ended up in the top 5. And it turned out Keras was the most widely used framework among winners. So it's not about the beginners, it's actually about the very best people. That's the people who stand to benefit the most from good design, from productivity, and from shorter iteration times, just because you can refine your ideas faster. And so one important question is, so now we have this focus on UX, but how do you achieve good UX and ease of use and productivity when you have user profiles that are as different as a first-year grad student or a Kaggle grandmaster? Well, so a key design principle that we've been using in Keras is progressive disclosure of complexity, right? Because Keras is a large and very diverse user base. It doesn't force you to follow a single true way of building and training models. Instead, it enables a wide range of very different workflows from the very high level to the very low level, which correspond to different user profiles and different use cases. So you could be using Keras like you would use scikit-learn, for instance, by just calling fit and letting the framework do its thing. Or you could be using Keras more like NumPy, so taking full control of every little detail, and anything in between, actually. And so you have a spectrum of workflows, and this spectrum of workflows is structured around 2 axes. There's model building, and there's model training. So let's take a look at model building. The simplest model you can build is just the sequential API. So you have very low flexibility because it's only good for a stack of layers. So one input, one output, and just a stack of layers. But it's also extremely easy to use. It's literally a list, so anyone can start using models like this. It's great for beginners. Now, if you want more complex topologies or maybe shared layers or models with multiple inputs, multiple outputs, but you still don't want to write everything from scratch, you still want to take a kind of like Lego-like scikit-learn style approach, you have the functional API. So that's great for most people, actually, in particular most engineers. So in that workflow, so you have much greater flexibility, right? But it's still very much a framework with some assumptions. And then you can gradually customize that and write more logic of your own by adding your own custom layers, your own custom metrics, custom losses. So it's really like progressive disclosure of complexity. You have this series of steps, and at each step, you're taking charge of more things yourself. You have more responsibility, basically. And now if you're a researcher, well, we also enable full subclassing, in which case you have total control of everything you're doing. It's much harder, and the risk of making a mistake is much higher. So it's slightly harder to debug, but it gives you total flexibility. And all of these different models, they can all talk to each other because they are built on top of the same API surface. They're basically the same objects, right? So you don't have silos, where on one hand you have the NumPy-like stuff, on the other hand you have the scikit-learn-like stuff. You really have this workflow. And another axis of this progressive disclosure of complexity is model training. Like the simplest way to train a model is just to call fits, like in scikit-learn. Like anyone can do this. And then you can further customize training by adding callbacks. Like a callback is this object that you can use to do specific actions at different points during training, like saving models, modulating your learning rate, and so on. But then again, the fit method only covers supervised learning use cases. So if you don't have the supervised learning use cases, maybe you're doing similarity, metric learning, maybe you're doing reinforcement learning, maybe GANs, and so on, well, you can very easily write your own custom training loops. And the lowest level at which you can do that is you manipulate the gradients directly with the gradient tape, right? And if you're doing that, you can basically implement whatever you want, including a new optimization algorithm or something like learning to learn, like a differentiable optimizer and so on. So basically very completely arbitrary research use cases. And so you basically have this spectrum of workflows from the very basic, the scikit-learn-like stuff, to the very advanced, like arbitrary research use cases. And that's our philosophy. And that's a philosophy that's not unlike that of Python itself, right? If you look at programming languages, you have some languages that are very prescriptive. They give you one way to do things, like Java is all about object-oriented programming, and some other languages are all about functional programming and so on. And Python is not like that. Python is a multi-paradigm language, right? And that makes it suitable for very, very different workflows, from just scripting, system administration, and things like data science, machine learning, or web development, right? And that's really possible because you have this multiplicity, this spectrum of workflows, right? And likewise, you can think of Keras as the Python of deep learning. Sure, it's great for beginners like Python, but it really offers you this spectrum of different workflows for different use cases and different user profiles, much like Python. And one important outcome of this philosophy is that you're avoiding silos, because silos are bad, right? You don't want to be in a world where there would be three incompatible ways to use deep learning, three API silos, with on one hand you have the high-level API, which is very inflexible, where you're just manipulating built-in features, which is also very easy to use. And on the other hand, you have the very low-level API, where you're writing everything yourself from scratch, which is very flexible, but is only accessible by experts. So instead, you want this spectrum where everything can talk to everything else, from the very simple and accessible to the very advanced and flexible, right? And with Keras, you have no API silos, right? And that means that everything you're learning as a student is still going to be relevant when you've become an expert or a researcher, right? You won't have to switch to an entirely different framework once you've reached a specific threshold of expertise, because that wouldn't actually make any sense. OK, so as I was saying, Keras is turning 5 years old next month. And so what about the next 5 years? You know, what will Keras look like in 2025? What are we building next? So the question that we should really be answering is, where is the world headed? Like, where is deep learning headed? What are the trends? And what can we do to make these trends happen faster, to create the most value for the industry and the research community? Because as tool makers, that's really our goal, right? We're trying to make the future happen faster, so we need to be able to read the trends and anticipate them. And there are 3 different trends I'm seeing. So one trend is towards more automation and even higher level machine learning workflows. Because today, engineers and researchers are still tuning lots of things by hand through trial and error. And tuning things through trial and error is not really a job for humans. It's a job for a search algorithm, or maybe for gradient descent. So I think we're going to see a move towards automated hyperparameter tuning, automated neural architecture search, and even eventually end-to-end automated workflows. And another trend, and that's something that's really universal in computer science, in the software industry, is a trend towards faster specialized chips and towards distributed computing at an ever larger scale, right? And also a move towards the cloud. Like, workflows that used to be run on local hardware are moving to the cloud. And so that's not specific to deep learning, right? That's really something you're seeing throughout the entire software industry. And the last trend, and I think that's the most important, is that we're still only using deep learning for a tiny fraction of the problems you could solve with deep learning, right? Maybe 10% or lower. And actually, deep learning is applicable to a tremendous amount of problems in every single industry. So I think over the next 5 to 10 years, we're going to see deep learning move out of the lab, out of the research lab, and into the real world more and more. We're going to be tackling the remaining 90% of problems that you could be solving with these technologies. Because ultimately, that's the point, right, of everything we've been doing. So the first trend is about automation. Like, today, the majority of deep learning research is still very much about fiddling with hyperparameters. And that's about to be pretty much obsolete. It's not going to happen overnight. It's going to be gradual. But it's going obsolete. Because that's not a job for humans, fundamentally. Humans are just not very good at it. And so in the next 5 years, we are going to see this move to, beyond handcrafting architectures, beyond manually tuning your learning rate and so on, and constantly fiddling with trivial configuration details. So machine learning will become increasingly higher level. And if you think calling model.fit is high level, it's not actually very high level. It's still fairly low level, because there's still a tremendous amount of decisions you have to make on your own, and that you need real expertise to make. So that's still way too low level. We're going to move towards workflows that are much higher level, things like end-to-end AutoML. So in the far future, maybe 5, 10 years from now, you can imagine that we're going to have APIs that look roughly like this. The input that the user is going to be providing is something like some data, the metrics they want to minimize or maximize, and domain knowledge provided in some form. And then you're going to have an end-to-end search process that's leveraging domain knowledge about deep learning, things like architecture patterns and so on. That's also leveraging pre-trained models and features from feature banks to find the best model. And that's not going to be a black box search process, because that would be kind of useless. It's going to be a white box search process. So it's going to give you visualizations to help you understand what's going on. And it's going to give you a way to provide your own input into this search process as it's happening. So it's really going to be a feedback loop, kind of like a dialogue between the user and the search process, right? And what you get out of it is a model that's ready for production, ready to deploy. So of course, this is not going to happen overnight. what we are doing with the Keras project today is not actually building this exact thing, because I think we are not quite ready to build it. Instead, what we are focusing on is building solid foundations that will eventually enable this system. Such a system is going to be built on top of foundations, and that's basically what we're trying to establish today. And the first layer of such foundations is this project, Keras Tuner. So Keras Tuner is open source. We released it a few months ago. It's already fairly mature. We're using it a lot internally. It's this very general, flexible, very scalable hyperparameter tuning framework. And so it's made primarily for Keras, but it's actually pretty general, so you can use it with scikit-learn, with XGBoost, and so on. So it supports a bunch of built-in strategies. The most popular is hyperband, and it makes it very easy to also define your own strategies if you're a researcher doing research on hyperparameter tuning, for instance. And one thing we're adding as well is tunable models, because it turns out it's very tough to craft appropriate search spaces, right, for different use cases. So what we are doing is that for popular use cases like image classification, for instance, we're giving you these pre-made search spaces, these templates almost, and you just add data, right, and the search proceeds, and then you get a model that's pretty good out of it. And the next layer of infrastructure for AutoML, for automation that we're building, is AutoKeras. So AutoKeras is an AutoML library that completely handles the model development part of the machine learning workflow. So it's still fairly experimental, but it's getting increasingly more mature. So what it does, it's going to analyze your data set. It's going to determine the best approach to go for your problem, things like architecture family and so on. And it's going to be running a neural architecture search and hyperparameter tuning to find the best model. And in the future, it's also going to be leveraging pre-trained models to do transfer learning and feature banks and so on. And so it has 3 different APIs you could be using. The highest level API is the task level API, where it's very scikit-learn-like. You just have classes like image classifier, text classifier, and so on. You just call fit on them. It gives you a model. We also have a lower level block level API, which is basically this very flexible language where you can inject domain knowledge about how you want the AutoML neural architecture search to proceed. And so the second trend I was mentioning is we're moving towards ever more parallel chips and more of them. So larger scale distributed training and cloud-based workflows. So in the future, it's going to be as easy to start training a model on hundreds of GPUs as it is to start training a model on your local CPU right now. So you're going to get quicker iteration cycles, right? And you're not going to have to build your own data centers. You'll be able to access large-scale remote resources without any friction. And so what we are building towards that. So you remember the loop of progress I was talking about. Like the quality of your ideas is a direct function of the speed at which you can iterate through this loop. And so you start from an idea, and then you have Keras. So Keras is very proactive, so you get to an experiment very quickly. But once you've done that, the bottleneck, the next bottleneck, is the speed at which you can run your experiments. And that's where ease of use of distributed cloud computing comes in, right? With faster hardware and making it faster to access cloud infrastructure, we're going to be cutting iteration time. That's why it matters, right? We are accelerating progress. So what we are doing on the Keras side to make this happen faster is this new project called Cloud Keras. So it's actually the first time I'm introducing Cloud Keras. It's a new API we are launching, which is currently in private beta. So you're going to be able to use it within a couple of months, probably after the Tensorflow Dev Summit. And so here's how it works. Suppose you have a script that trains a model, and you've debugged it locally, maybe on your laptop or on a Colab notebook, on a free GPU instance. And it's running. But the problem is you have hundreds of gigabytes of data. It's going to take 3 days to train your model on a single GPU. So you want to train as fast as possible. So what do? you just add one line of code at the top of your script, and that's this line, keras.cloud.run with some config. So if you expand it, it becomes the thing you have on the right. And you just rerun that cell in your notebook or just rerun your script. And suddenly what's happening is that the same script that was running locally is now running on 8 workers on GCP with 4 GPUs per worker. So you have your model running on 32 GPUs with basically no added effort compared to just running it locally. So we are really cutting the friction there is in using distributed training in the cloud by like an order of magnitude. So we think this is a really, really cool product. We've been using it a lot ourselves. So what this one line of code does is it will collect your script and all its dependencies. It also gives you control over how you want that to happen. So it's very flexible, very configurable. It will inject a distribution strategy, right, into your script. So you don't have to worry about that. You can also configure that manually if you're doing something special, right? It's going to be creating a Docker image with all this stuff. It will spin up machines in GCP corresponding to the config you've passed, and it's going to be launching your Docker image on these machines. It's going to start training, and it will stream your logs to a remote directory of your choice. So that's where your saved models are going to be saved and so on, and everything you're doing with callbacks. That's also where your TensorBoard logs are going to be stored. So you can just, if you want to monitor training, you can just point a TensorBoard instance to that directory. And so it works for all kind of hardware. It's going to be working for multi-GPU. It's going to be working for TPUs, even a TPU pod. And so it works for all kinds of workflows as well. You could just be having a fit-based workflow or custom training loops. And importantly, it also works well with Keras Tuner. So imagine doing distributed hyperparameter tuning in the cloud on like hundreds of GPUs without any friction compared to just launching a tuning run on your laptop. So this is currently in private beta. It will be shipping in a couple of months, probably after the Dev Summit. And so the last train I wanted to talk to you about is moving deep learning, machine learning into the real world, right? So research labs are increasingly not where the cool stuff is happening. Like personally, I think spending $1 billion to train big RL models to beat some benchmark is not very cool. And you know what's cool? What's cool is deploying machine learning into the real world, like deploy ML to every problem it can solve out there. Because I think so far we've only scratched the surface. We've been tackling maybe 10% of the problems we can solve, right? So the first thing you need is you need to make models more portable. So it should be possible to save a deep learning model from a notebook and then load it up in a web browser, load it up on a microcontroller and so on. So running anywhere, portable models, not just inference, but also training. And so what we're doing to make models more portable, well, the first thing, something we've shipped recently, so it's shipping in Tensorflow 2.2, which is going to be available in about a month, is a complete rework of how we do preprocessing in Keras. So we are taking the stance that preprocessing should be done as part of the model, right? Because otherwise, a problem you're facing when you're trying to deploy a model, like let's say you want to deploy your model in a web browser, is that you have to re-implement the input pipeline in JavaScript this time. And it has to be the exact same pipeline. Because if you make the slightest mistake, your model will be broken. And maybe it will be silently broken. Maybe your metrics are going to be lower than they should be because you make a slight mistake in the input pipeline. So your model is not looking at the correct distribution. So what we're doing is we're introducing a new set of layers that do pre-processing as part of the model. And they're serializable, so they're fully portable, right? So that covers things like text vectorization, things like tokenization, indexing, even computing n-grams, and so on. It also covers image use cases, structured data. Right, so you're going to get models that are end-to-end models. They ingest raw strings or raw images, and they give you predictions. So fully portable end-to-end models. And another thing we are doing is that we're really betting on TF Lite for mobile devices and TensorFlow.js. for deep learning in the browser. We really believe that the ability to run deep learning in the browser, in mobile devices, at production level performance is really a game changer. It enables a huge range of new applications that were not possible before. So here are a few examples. Last year, Google released its first AI-powered Google Doodle, which was the Bach music synthesizer thing. And so 50 million people over 3 days have used it to make their own music, save it, share it, and so on. We also have pre-trained models in JavaScript that enable you to do things like face morphology tracking, to do things like person segmentation, and so on. And this really enables a bunch of cool augmented reality applications. And one last thing we're doing to make models more portable is our model optimization toolkit. So it's a set of utilities that can dramatically reduce the size, the memory consumption, and the compute intensiveness of your models, especially for inference. And that's especially important if you don't want to drain your user battery or you want to run in a very resource-constrained environment, like a microcontroller, for instance. So one thing you can do is post-training quantization, right, where you're switching the weights of your model from float 32 to integer 8, right? And so compared to the float version, your quantized models can run 2 to 4x faster, right, on CPU, and they're 4x smaller. Another thing you can do is pruning-aware training. So weight pruning is about inducing sparsity in your model, so setting most weights to 0. And you can very easily get to 90% sparsity, so models that are 10x smaller. But to do that, you have to run pruning-aware training. You cannot do it as a post-training step. And so we offer you a Keras API to do just that. So pruning up to 90% sparsity at a very small loss of accuracy by using this pruning schedule that works with fit. So you have these 3 trends to conclude. A move towards more automation and higher level workflows like AutoML. A move towards larger scale distributed training, including hyperparameter tuning in the cloud. And a move towards machine learning in the real world, like portable models, more efficient models, real world deployment, being able to run models everywhere. And there's a lot of synergies between these trends. Like for instance, the move towards automation is making machine learning more accessible, right? Making cloud computing easier to use is also making machine learning more accessible. You can train a large-scale image classifier in a matter of minutes instead of a matter of days. And you don't need an engineering team to do that. So that's really making machine learning more accessible is really accelerating the move of these applications to the real world. Because right now we are living at this very interesting, this transformative moment, right? Where machine learning is, we're increasingly realizing that machine learning can actually solve problems that for years we thought were impossible. And we've really just started leveraging that potential. And we are not going to reach the full potential of AI if we're waiting for researchers, at companies like Google or Amazon or Microsoft or whatever, to solve problems that people have. Because often, in the tech bubble, we are not aware that these problems are even problems. Things like optimizing fish farming in Norway with deep learning, or things like monitoring illegal logging in the Amazon rainforest. We're not even aware these are problems. So we shouldn't rely on Silicon Valley, basically, to solve them. Instead, what we should be doing is making deep learning, making these technologies radically accessible. Making it usable by anyone with some coding skills and an idea, because then these people who are familiar with the domain, who are familiar with these problems, are going to be able to solve them on their own, right? And that's how you can realize the full potential of AI. Thank you.